Hello everyone, my name is Adila and Emily and I are going to be presenting our project discussing the effect of increasingly asymmetric bilateral auditory rhythm on subject sensorimotor abilities. Now, rhythmic stimulation is often used to treat gait impairments, especially hemiplegic gait. Now, what is hemiplegic gait? Hemiplegic gait is a type of gait impairment mostly caused by stroke that starts with damaged neurons leading to abnormal gait patterns causing abnormal muscle tone, which is also the cause of further gait problems. Some common symptoms include hip circumduction, where you kind of move your impaired leg forward and outward, knee flexion, where you're unable to bend the knee as far back as the healthy limb, limiting your range of motion by a lot. Another very common symptom includes flat foot drop, where instead of striking your heel against the ground while walking, one tends to drop their foot flat against the ground, mainly due to lack of control.
Now, an important question to ask about rhythmic stimulation is, why does it work? What is the justification for using this? Now, according to a study by Menka, significant differences of gait speed and cadence, which is the steps per minute, were found between groups receiving rhythmic stimulation therapy in comparison to neurodevelopment treatment and treadmill training alone. An increase of gait velocity often means that there will be a decrease in step time, as shown by the equation. Now, there are four main models of variable rhythmic stimulation that we will be observing and testing in our trial: linear ratio, linear step time, discrete ratio, and discrete step time. Now, these make up two main parameters, which would be linear versus discrete and ratio versus step time. Linear and discrete basically mean a linear model will be a gradual change over time, whereas discrete will be like stair steps. Then the ratio is defined as the right step time divided by the left step time, whereas the step time merely addresses the amount of time that the step from footfall to footfall is. Now, this table compares the four models, as I was mentioning in the last slide, in a little more easier to understand way. You can see that the rate of change of ratio is going to be linear for the linear ratio and the discrete ratio models, and it's going to be logarithmic for the linear step time and the discrete step time models. And for the discrete, obviously it's going to be discrete, meaning the stair step pattern, and the linear is going to be continuous. And you see that also in the rate of change, that the linear ratio and the discrete ratio will be logarithmic, whereas the linear step time and the discrete step time will be linear. Now, that is basically just because if we're measuring ratio, then the models that measure ratio will be linear. If we're measuring step time, then the models that measure step time will also be linear. And we can see that for the two discrete models, they are both abrupt, meaning the stair-step model will result in abrupt changes in tempo instead of continuous or smooth changes in tempo as seen in the linear models, meaning someone will be walking, and in the linear models, it will be slowly and gradually changing in tempo, whereas the abrupt will all of a sudden change in tempo. Now these are two more graphs that expound on the table we saw 2 slides ago. And these measure time against step time. And you can see it's divided up to left step time and right step time. Again, we see discrete models have a stair-step pattern, whereas linear models are more of a linear or straight line sort of model. And we see that since we're measuring step time, the models that measure step time are more straightforward, whereas the ones modeling ratio are more curved. And we also see that the left step time is decreasing, whereas the right step time is increasing, and that is a big part in our study. So now that you know a little bit more about the basics of the 4 models that we're going to be testing, it's good to know the process of rhythm entrainment. It has 3 steps, the first of which is perception. This is where the subject perceives a change in time or tempo according to their JND, which is their just noticeable difference, and we'll cover that in just a few slides. Basically, this person notices there's a change. Then comes prediction. The subject predicts the next beat depending on the rhythm or tempo. This person says, I think the next beat is going to be just about now. Then there's the third, last step, which is reproduction, where the subject reproduces the rhythm in their gait pattern, where they perceive that there is a certain tempo, they predict the next beat of the tempo, and then they produce that tempo by putting their foot down in this case. Ideally, a subconscious response would skip the prediction step. It would go straight from perception, there's been a change, to reproduction, I'm doing this. It's more of a subconscious response. You're not really thinking about it. And eventually, in future studies, subconscious responses could be measured based on response time being within 3 standard deviations of that person's personal just noticeable difference. Again, we'll explain that in just a few slides. Now I'd like to go over some of the nitty-gritty of what really happened in this experiment. Now, the first and foremost thing that we did was we received each participant's informed consent. We brought them into the lab, we showed them around, we told them roughly about what the experiment was about, what was going to be expected of them, and what the dangers could be in taking part. And once we received their informed consent, we were ready to proceed with the rest of the experiment. We started off by measuring their just noticeable difference, which we did by playing them 2 beeps with a pause in between and asking them to compare the length of that pause with another set of 2 beeps with a pause in between, which could be longer, shorter, or the same duration as the first pause. And that was gave us the information to measure their sensory perception. Then we had them go ahead and step on the treadmill, and we found their comfortable walking speed. We did this by starting at a fairly low speed, and at the participant's request, we increased the speed gradually until they felt that they were at a comfortable pace where they weren't walking too fast or too slow, and they felt that it was a speed that they could walk at for roughly 6 minutes at a time. Then we had them step off the treadmill, and we placed 11 reflective markers over their lower limbs. These included, the sides of their knees, their hips, their sternum, parts of their heel, toe, and ankle. And we had them step back on to the treadmill and perform a baseline test. This was to obtain their comfortable step time and to basically see overall, using their reflectors and cameras that are built into the system, how do they walk normally at this particular speed. Then we were ready to perform the 4 trials, which consisted of the 4 models that I spoke about before. with breaks in between, of course. And these trials were performed in a randomized order using a Latin square. This was done to get rid of some of the error that would possibly pop up. For example, if we were to see in our results that every participant did not do so well in the fourth trial, then we could know that it wasn't because it was perhaps the last trial for every single person because we mixed it up in order. Maybe the fourth trial would be first in order for someone or third in order for someone, and we could know it wasn't because perhaps they got very tired by the end of the experiment. We could know it was because of a significant difference of the model itself. Now, as you proceed to the next slide, you're going to watch a video demonstration of just a few seconds of someone walking on the Karen treadmill system. And as you can see in this video, it's going to be pretty far along in one of the trials where the cues started out being left, right, and the asymmetry was increased so much that by the time this video was taken, the left and right cues were almost identical, almost seemed like they were one word. So you will be able to see that in the next slide.
Before we move on to the results section, we should probably go over some of the key assumptions we made while putting together this trial. First one is that the baseline speed that the participant chooses will actually be their comfortable speed throughout the duration of the study. That is not actually true because when people are walking over ground, their comfortable speed tends to change depending on their fatigue level, the type of ground they're walking on, and many other factors. That's one assumption. The second assumption we made is that the subjects do not have any form of undiagnosed gait impairment. Although we did ask our subjects if they've had any kind of surgery or accident, stress fracture, anything like that, they could still have undiagnosed issues that we don't know about, so we just assumed that they don't have any issues with their gait. The third one being that their stride time remained constant throughout the study, which again is variable. So those are the three assumptions we made before putting together this trial. So the results were quite interesting. We were able to generate some key findings regarding their trend, the synchronization error, and especially the maximum achievable step time asymmetry, which was within the 30 to 42% range and seemed to be pretty consistent among several subjects that were not all achieved at the same time, but it was within a very close range. We will have to do further statistical evaluation in order to make sure that it is, in fact, consistent between subjects. As you can see on this slide, the trends are quite visible, I would say. You can see that the error between the required asymmetry and the achieved asymmetry are increasing over time. However, the overall trend seems to remain the same. I know in the first graph it kind of appears that it's kind of a straight line, but it's not. It's an exponential curve, but the gradient it's very, very subtle. That's how that it is. And both of those curves showed maximum achievable step time asymmetry of around 33.5, 33.6%. So that just proves that the effect of transition, whether the transition of asymmetric, the asymmetric transition is small or very big, like in the discrete model, their maximum achievable asymmetry isn't majorly effective. Of course, we'll know better once we try it out on several other subjects, but so far this seems to be the trend. The results of the linear models were similar to the exponential model. The trend is the same between the continuous and the discrete models, which leads me to think that even though subjects are not able to sync up with the cues in the way that we were hoping they would, they're still able to understand the difference in the overall trends, like is it exponential, is it linear, or is the asymmetricity increasing slowly or quickly. Also, it may not be obvious here, but their standard deviations in the achieved asymmetry were very different, which leads me to think that it might have been easier for them to adjust to one model more than the other. But of course, we'll know better after statistical evaluation, checking to see if the results are consistent between different subjects. Another thing we had expected was that the adherence to the cues would decrease over time, meaning the errors would get larger and larger as the frequency of the cues increased. Subjects were having difficulty keeping up with them at higher tempos because by the time they stepped on the treadmill, they would hear the other cue. In some cases, it might be easier for subjects to sync up with smaller increments, like when the tempo is increasing very, very slowly over time to an extent where they don't notice it almost. But that's a conversation for a different project. The overall synchronization error trend was quite interesting to see because we had expected that it would grow larger over time, meaning it would become harder for subjects to predict and expect cues, but they seem to be able to sync up with the cues much better over time, and towards the end they even started predicting the timing of the cues. As you can see in the graphs, it's when the errors started becoming negative, when they were less than 0, that's when subjects were like, okay, the cue is going to drop, I'm gonna step my foot now. So with regard to future work, there is a lot to be done in order to make this project well-rounded. Before anything else, we need many, many more subjects. We'd like to extend cueing modality from auditory to tactile and visual. We know for a fact that auditory cueing is, when it comes to temporal perception, aka the perception of time, it's dominant over tactile and visual, but we'd like to see if those other modalities, tactile and visual, if they have other strengths that auditory stimulation does not. Number 3, we want to see if there's any effect of limb dominance on the gait pattern, meaning do subjects do better with some things than others when it comes to gait? Are they syncing up better or worse? Are they particularly effective on the faster limb than the slower limb, depending on which side is more dominant? We would like to explore that too at one point. Number 4, the learning effect of gait from rhythmic adaptation. So far, for this project, we did randomize our subjects, which means that any trend we see between subjects is not from any kind of learning effect, or at least it's minimized as much as possible. However, we would like to look at the results, go, okay, this was done first, second, third, fourth, and try and see if there's any difference between those trials, irrespective of what models they were put in, to see if there were any effects from just learning the trends and how the system works. Another thing we would like to look at is explore the possibility of an asymptote, which would be indicative of the subject's overall ability to respond to rhythmic cues. This means that we would look at their synchronization error and try to find the point after which it becomes kind of constant, that okay, after this they're neither able to sync up with the cues nor predict them. So we would like to explore that as well. And of course, before doing anything else, we would need to perform statistical evaluation to find out if our results are significant or not. Thank you for listening, everyone.